The construction and assembly of the Vidalta Bridge in Mexico City stand as a remarkable feat of engineering and planning, showcasing the ingenuity required to overcome the unique challenges posed by its location. Situated within a steep wooded ravine, the bridge's design and construction demanded meticulous attention to detail. The Vidalta Bridge, a two-span cable-stayed bridge with a distinctive harp system, was conceived to stretch across a considerable 240-meter span between a building and an opposing abutment. Yet, during the design phase, engineers grappled with a significant challenge: the uneven distribution of spans. Initially, the possibility of establishing a support at a distance of 60 meters from the building was considered, resulting in an imbalance between the two spans 60 meters and 180 meters respectively. To rectify this disparity, an inclined tower was ingeniously incorporated into the design. This tower, set at an incline, not only divided the deck into two stretches measuring 78.5 meters and 161.5 meters, but also facilitated a harmonizing of the spans. Even with this ingenious solution, there remained a substantial discrepancy between the two deck stretches. To rectify this, a compensation span, fabricated using concrete, was introduced. This span, positioned between the two stretches, acted as a counterbalance due to its inherent heaviness. Contrastingly, the main span was crafted from lightweight steel. This astute design decision contributed to load distribution balance within the stay cables and the overall stability of the tower. A fusion of materials formed the backbone of the Vidalta Bridge's construction. The bridge primarily relied on a steel-concrete hybrid system. This integration of materials harnessed the durability of steel and the solidity of concrete. The deck, 1.50 meters in depth and 13 meters in width, was designed to accommodate two lanes of traffic, striking a harmonious balance between functionality and form. The construction process unfolded in several sequential stages. Foundational work set the stage, creating a robust underpinning for the tower and abutments. The tower itself, with its distinct incline, was constructed using steel sections and fortified with concrete. These measures laid the groundwork for the subsequent phases. Off-site fabrication of deck sections paved the way for their transportation and eventual installation. The main span steel components were meticulously assembled and linked to the tower. Simultaneously, the concrete compensation span was poured in situ, ensuring both its weight and stability. This process hinged on precise engineering and impeccable coordination, pivotal to attaining the desired alignment and structural integrity. Once the deck sections were firmly in place, the intricate cable stay system was introduced. The cables, fastened to the tower and anchored to the deck, provided the essential load distribution and support that the bridge required. The implementation of the harp system, characterized by numerous cables radiating from a central point on the tower, not only enhanced the bridge's structural efficiency, but also contributed to its aesthetic appeal. Completing the masterpiece required the meticulous installation of safety barriers, lighting, and road surfacing. A comprehensive series of tests and inspections ensured that the bridge conformed to the highest safety and quality standards, ensuring the well-being of those who would traverse it. The Vidalta Bridge emerged as a triumphant testament to the tenacity, skill, and creative problem-solving capabilities of the engineers and construction teams that brought it to life. Overcoming the challenges posed by the rugged ravine and uneven spans, the bridge not only stands as a functional transportation conduit, but also seamlessly integrates with its natural surroundings, leaving an indelible mark on Mexico City's landscape. The Marlee and Duffs bridges, located over Dingo Creek north of Wingham, were iconic timber truss bridges that had long served as vital transportation links. Due to the high maintenance requirements and considerable budget expenditure these bridges demanded, the Greater Terry City Council undertook a significant project to replace them. The endeavor involved the demolition of the old timber bridges and the construction of two new 3-span, 2-lane concrete bridges. This comprehensive initiative encompassed not only bridge construction, but also included associated approach roadworks, road pavement, drainage systems, and various ancillary tasks. The entire project, from initial options assessment to final execution, showcased the substantial benefits of effective project management. Early in the project lifecycle, program and cost estimates were meticulously developed. This level of planning played a pivotal role in the success of the project, with positive impacts seen in terms of cost effectiveness, construction quality, safety, and adherence to the established timeline. Duffs Bridge, which had stood since 1926 as an Allen Truss Bridge, was among 105 similar bridges built across New South Wales. Over the decades, it had provided a crucial connection to key areas like Elands, Ellenborough Falls, and the agriculturally fertile volcanic soils of the Bulga Plateau. However, the bridge was now approaching the end of its serviceable life. In an effort to prolong its utility in the short term, weight restrictions were imposed in 2009 or 2010, and speed humps were introduced to regulate traffic speed to a mere 10 kilometers per hour. In 2010, a temporary closure of the bridge necessitated a 13 kilometers detour for commuters. Interestingly, the community witnessed the removal of the speed humps shortly after their installation. Some locals interpreted this act as irresponsible, fearing that without these traffic calming measures, the community could face further inconvenience and isolation if bridge closure became inevitable. The bridges, both Duffs and Marlee, held historical significance to the community, making their removal a contentious option. The recognition of their historical value raised questions about the appropriateness of complete removal. Despite this sentiment, both bridges were in dire need of renovation or replacement, a sentiment shared by numerous wooden bridges across the Manning Valley that supported local communities. Duffs Bridge specifically was an Allen-type timber truss road bridge with a single timber truss span measuring 27.4 meters, QOH. The bridge featured 3 timber approach spans on one end and 2 on the other, culminating in a total length of 69.5 meters, 228 feet. The superstructure of the bridge was supported by timber trestles and accommodated a single-lane carriageway with a minimum width of 4.6 meters. To ensure safety, a timber post and rail guard rail extended along the full length of the bridge. The construction of the new concrete bridges marked a significant departure from the traditional timber truss design. Concrete bridges offer enhanced durability, reduced maintenance demands, and improved load-bearing capacity, making them ideal for modern transportation requirements. The replacement bridges consisted of 3 spans each, accommodating 2 lanes of traffic, thus addressing the need for improved transport capacity over Dingo Creek. The successful completion of this project underscored the advantages of adept project management in terms of cost savings, construction quality, safety compliance, and adherence to project timelines. While the historical significance of the old timber bridges was recognized and valued, the pressing need for renovation or replacement could not be ignored, given their deteriorating conditions and the evolving transportation demands of the region. By embracing modern concrete bridge design, the council secured a more sustainable and efficient transportation infrastructure for the community. This project serves as a testament to the careful balance between historical preservation and practical progress that local authorities often strive to achieve.
The replacement of Duffs Bridge and Marlee Bridge by the Greater Terry City Council was a complex and innovative project that aimed to address the challenges posed by the deteriorating condition of the original timber truss bridges. These historic structures, handed over to the council in 1989, had gradually become costly and labor-intensive to maintain due to the quality of timber used and the skilled labor required for upkeep. The adverse condition of the bridges also led to load limits being imposed on them, impacting local rural communities. In response to the need for an upgrade, the council, supported by community and business lobbying, secured funding to undertake the ambitious task of replacing both bridges. The project management process was intricate, marked by multifaceted considerations arising from site constraints, construction techniques, and paramount safety concerns. To streamline the construction process and minimize disruptions, the decision was made to prioritize the replacement of Duffs Bridge. This strategic choice not only facilitated construction logistics, but also allowed the project team to apply lessons learned from Duffs Bridge to improve the replacement process for Marlee Bridge. The project was underpinned by a comprehensive options report and thorough site investigations, which guided the selection of a similar design for both bridges. Opting for a consistent design simplified the construction process and effectively lowered costs. This approach was rooted in practicality and efficiency, ensuring that the project remained on track while adhering to budget constraints. The demolition of the old timber truss bridges was a meticulously planned endeavor, driven by safety considerations and the unpredictable behavior of deteriorated timber trusses. Specialized cranes were enlisted to delicately lift and disassemble the spans, taking into account the delicate state of the timber and potential hazards. The experiences gained during the demolition of the first bridge were instrumental in refining the process for the second bridge, reflecting a commitment to continuous improvement. In terms of construction, the project embraced innovation and modern design techniques. The use of precast components, such as pre-stressed concrete planks, represented a departure from the traditional methods employed during the era of the original timber bridges. These concrete planks were equipped with transverse post-tensioning bars, a clever engineering choice that allowed for immediate traffic utilization following installation. This innovative strategy significantly reduced the inconvenience to the community by expediting the integration of the new bridges into the transportation network. In the pursuit of constructing infrastructure that would endure the test of time, the Greater Terry City Council displayed its unwavering commitment to innovation and quality. This commitment was especially evident in the meticulous attention given to the durability of the new bridges, exemplified by the introduction of a double corrosion protection system for the transverse post-tensioning bars. The decision to implement a double corrosion protection system was a result of foresight and a proactive approach to addressing potential future challenges. Corrosion, a natural process triggered by environmental factors such as moisture, salts, and pollutants, can significantly compromise the integrity of metal components over time. This is of particular concern in bridges, where metal elements are exposed to the elements and can be vulnerable to rust and deterioration. To mitigate the risks posed by corrosion and ensure the longevity of the newly constructed bridges, the Council opted for a dual-layered approach to corrosion protection for the transverse post-tensioning bars. This innovative strategy involved the application of two distinct corrosion-resistant measures, each reinforcing the other to provide enhanced safeguarding against corrosion-related issues. The first layer of protection likely involved the use of high-quality corrosion-resistant coatings. These coatings, which can include epoxy coatings or galvanization, act as a barrier between the metal surface of the post-tensioning bars and the external environment. They are designed to repel moisture and corrosive agents, effectively preventing them from coming into direct contact with the metal. This primary layer of protection significantly reduces the likelihood of corrosion initiation. The second layer of protection likely involved a cathodic protection system. Cathodic protection is an electrochemical technique that involves introducing a sacrificial anode, a more easily corroded metal, into the system. This anode, often made of materials like zinc or aluminum, corrodes preferentially in place of the transverse post-tensioning bars. As a result, the bars remain protected from corrosion, effectively extending their lifespan. This approach is particularly effective in environments where corrosion is a major concern, such as bridges that are exposed to harsh weather conditions and corrosive agents like saltwater. By implementing this dual-layered corrosion protection system, the Council showcased its dedication to providing a robust and enduring infrastructure solution. The forward-thinking engineering approach demonstrated an understanding of the challenges that infrastructure can face over its lifetime and the proactive measures required to address them. Moreover, this attention to detail reflected the Council's commitment to not only meeting the immediate transportation needs of the community, but also ensuring that the bridges would continue to serve generations to come. It encapsulated the Council's philosophy of responsible stewardship over public infrastructure, where a long-term perspective takes precedence over short-term gains. Throughout the project, numerous challenges emerged, ranging from safety considerations to logistical complexities. However, each challenge was met with a commitment to innovation and creative problem-solving. The project's success can be attributed to the Council's ability to adapt and find solutions that address these challenges while staying true to the project's overarching goals. The Atlantic Bridge, a remarkable engineering feat completed in 2019, stands as a vital connection between the two sides of the Panama Canal in Colón, Panama. With a strategic position spanning the Atlantic entrance of the canal, the bridge plays a crucial role in enhancing local and regional connectivity. This architectural marvel is the third bridge to grace the Panama Canal, succeeding the Bridge of the Americas and the Centennial Bridge, both located on the Pacific side. The Atlantic Bridge showcases an innovative design, characterized by its double-pylon, double-plane structure, composed of concrete girders and supported by cable stays. Its main span stretches an impressive 530 meters, 1,740 feet, flanked by two side spans spanning 230 meters, 750 feet each. The bridge's eastern and western approaches extend 1,074 meters, 3,524 feet, and 756 meters, 2,480 feet, respectively. This masterpiece of engineering was conceived by the China Communication Construction Company and brought to life by Vinci Construction, a French company known for its expertise in large-scale infrastructure projects. Functionally, the Atlantic Bridge serves as a crucial segment of a local connection road connecting Bolivar Highway in the east to an undeveloped western region. This modern marvel efficiently replaces the Panama Canal ferry, facilitating smoother and quicker movement for both vehicles and pedestrians. Notably, it stands as the sole bridge positioned north of the Culebra Cut, also known as the Puente Centenario. Cebu City, nestled within the captivating seascape of the Philippines, has become the backdrop for a remarkable feat of modern engineering that echoes the nation's historic navigation achievements. The Philippine archipelago, with its intricate web of over 7,000 islands, has a maritime history that oscillates between serene tranquility and tempestuous turmoil. One narrative in this seafaring saga speaks of the Tornaviaje, a treacherous trans-Pacific route that connected the East Indies to the Americas, birthed from Cebu's harbor in 1565. This voyage, laden with challenges and perils, marked not only a maritime triumph, but also a pivotal moment in the emerging global landscape. It knitted the Old World to the economy of the Ming Dynasty and the Americas, birthing a trade route that spanned over 250 years, the Manila Galleon Line, which traversed the boundless Pacific waters. Fast forward 5 centuries, and Cebu's storied waters now host a contemporary marvel that is redefining the Philippines' trajectory once again. The Asiona-built Cebu Bridge, spanning the channel that separates Cebu and Mactan Islands, this 2.5-kilometer cable-stayed bridge has an awe-inspiring 650-meter main structure that will facilitate an 8.5-kilometer highway, dissolving the chronic gridlock that has beleaguered these routes. The journey to realize this bridge was one of triumph over adversity, as engineers and operators surmounted logistical challenges scattered across the expansive Pacific nation. From orchestrating the movement of office computers to confronting a pandemic's disruption and a typhoon's devastation, the project was a testament to human ingenuity prevailing over nature's wrath. The Cebu Bridge is a work of grandeur and precision, boasting monumental statistics that include a main span stretching 390 meters between towering pillars and pylons that reach an impressive 145 meters in height. The foundation piles plunge a remarkable 60 meters beneath the water's surface, holding steadfast against tides and currents. A cornerstone of this project was the beam launcher, an Acciona innovation that enabled the construction of access ramps and slopes. This intricate rack and sprocket system, manufactured in Spain and transported for this project, exhibited enhanced control and precision compared to conventional winch and cable systems. It demonstrated its mettle by raising massive 110-ton beams spanning 52 meters and ascending gradients of up to 7%. China's high-speed railway system stands as a marvel of modern engineering, characterized by its extensive network of elevated rail routes comprised mainly of flyovers and bridges. These elevated tracks not only optimize ground space utilization, but also enhance the stability of the train journey, resulting in a smooth and efficient travel experience. China's unwavering commitment to expanding its high-speed rail network is evident in the ongoing construction of these elevated rail routes. Central to this infrastructure are the impressive box girders, which form the backbone of the bridges supporting the high-speed railway lines. These box girders, the major structural components, are a fusion of advanced materials and precise engineering. Manufactured from a blend of robust structural steel and durable pre-stressed concrete, these box girders are meticulously pre-engineered and prefabricated at dedicated production facilities. This off-site fabrication streamlines the construction process and ensures the highest quality standards are met. The transformation of raw materials into functional box girders follows a comprehensive, multi-stage process involving 18 distinct procedures. The intricate journey begins with the meticulous procurement of raw materials, which are then subjected to a series of exacting manufacturing procedures. These encompass shaping, reinforcing, and assembling the materials into the characteristic box girder form. Impressively, each box girder weighs a staggering 1,000 tons, a testament to the sheer scale of these engineering endeavors. Once ready, these colossal girders are transported to the construction site. Here, they undergo the final phase of assembly, where they are carefully bolted together. This on-site assembly culminates in the formation of a robust and stable foundation for the bridge. China's high-speed railway bridge construction encapsulates a fusion of meticulous planning, cutting-edge materials, and precision engineering. The elaborate process of turning raw materials into massive box girders, each weighing 1,000 tons, underscores the nation's dedication to pushing the boundaries of modern infrastructure. As China's high-speed railway lines continue to extend, these innovative elevated rail routes will remain an emblem of the nation's prowess in engineering and transportation.
This national primary road, serving as a vital transportation link, holds a significant role in the urban fabric of Cork City, Ireland. Designed as a partial ring road, it gracefully encircles the southern suburbs of the city, fulfilling a crucial role in connecting various important destinations and easing the flow of traffic within the area. With an expansive length of 15.45 kilometers, 9.60 miles, this road serves as a lifeline for the city's commuters, residents, and businesses. It efficiently weaves through the southern neighborhoods, fostering connectivity and accessibility. The road not only aids daily commuting, but also facilitates the movement of goods and services, thereby playing a pivotal role in bolstering the economic activities of the region. A notable feat in the road's development was the South Ring Road flyover scheme at Sarsfield Roundabout. The significance of this project was highlighted by the careful implementation of traffic diversions, ensuring the minimal disruption of normal traffic flow during the construction process. Central to this endeavor was the construction of a remarkable girder bridge, an engineering marvel that spans an impressive 39 meters in length and weighs up to a staggering 105 tons per individual girder. The construction phase witnessed the deployment of specialized equipment, underscoring the intricacy of the project. Two cranes, namely the CHL 350 and the formidable 500-ton crane, took center stage in the assembly process. These heavy-duty machines played an indispensable role in ensuring the safe and efficient installation of the flyovers. Their substantial lifting capacities facilitated the precise positioning of components, contributing significantly to the overall success of the South Ring Road flyover scheme. One of the project's standout accomplishments was the completion of a 2.5-kilometer, 1.6-mile flyover at the Kinsale Road roundabout, executed as part of the larger South Ring Road flyover scheme. This particular segment exceeded expectations, being finalized 6 months ahead of schedule. A significant investment of €55 million was allocated to the project, and the outcome was a comprehensive infrastructure upgrade that greatly benefited road users. The newly constructed flyover at the Kinsale Road roundabout introduced a host of advantages to the transportation landscape. With 3 lanes for eastbound traffic and 2 for westbound, the flow of vehicles was streamlined, drastically reducing congestion and delays. Moreover, the integration of 4 on-off ramps seamlessly connecting the dual carriageway to the roundabout ensured smoother transitions and enhanced accessibility for motorists. The benefits of this endeavor extended well beyond the realm of transportation. The positive impacts were visible in various aspects of the region's development. Reduced congestion translated to enhanced road safety, as the improved traffic flow minimized the likelihood of accidents and traffic-related incidents. The East Hampton-Mannan River Bridge, a crucial piece of infrastructure connecting communities, is undergoing a remarkable transformation. The Massachusetts Department of Transportation, MassDOT, has embarked on a project to replace the aging bridge, employing the innovative accelerated bridge technique. A significant milestone was achieved as 8 massive deck bulb T-beams were successfully installed, showcasing the power of engineering and coordination. This endeavor, facilitated by a colossal crane, unfolded over an intense 8-hour period, leaving onlookers awestruck by the intricate maneuvers and precision involved. The pivotal moment of the project arrived as the deck bulb T-beams, carefully sourced from Vermont, were delivered to the construction site. These mammoth beams, each spanning an impressive 93 feet and weighing a staggering 100,000 pounds, were poised to be the foundation of the new bridge. The logistical feat of transporting such colossal elements demanded the use of tractor trailers, which impeccably lined up in front of the bridge project area, ready to deliver their monumental cargo. Central to this operation was an imposing crane, a true marvel of modern engineering. With the power to lift these enormous beams, the crane played a pivotal role in the installation process. The endeavor commenced in the early hours of the morning, approximately around 7:30 to 8 o'clock. The scene was one of orchestrated chaos, as the specially designed platforms of the tractor trailers gently lowered each beam into the waiting hands of the crane. Measuring and alignment were of paramount importance in this endeavor. The meticulousness of the engineers and workers was evident as they meticulously gauged and adjusted distances, ensuring that the placement of each beam was immaculate. The first beam installation, albeit time-consuming due to the careful adjustments, set the tone for the sequence of events that followed. Guided by the Y ropes that offered stability and control, the first beam was gingerly lifted into place. The effort put into its placement was a testament to the complexity of the task at hand. As the morning progressed and the installations continued, a sense of rhythm began to emerge. The 7 beams that followed were positioned with more fluidity, reflecting the growing familiarity of the team with the process. By the time the 7th and 8th beams were positioned, the orchestrated dance between the crane, the beams, and the workers became a symphony of efficiency. Despite the onset of rain around 1 o'clock in the afternoon, the operation pressed on unfazed. The rain was a mere backdrop as the team focused unwaveringly on the task at hand. The seamless handling of the beams continued, a testament to the skill and experience of those orchestrating this intricate ballet of engineering. The magnitude of progress achieved during the day was evident as the 7 beams took their places, forming the skeleton of the new bridge. From the morning's assembly line of beams to the afternoon's span of connected structures, the transformation was undeniable. The bridge's form began to emerge with each precise placement, showcasing the tangible outcomes of the day's efforts. The climactic moment arrived with the installment of the 8th and final beam. By this time, the rain had failed to dampen the spirits of the workers and bystanders alike. The sight of the massive crane hoisting the last beam into place was a testament to human ingenuity. The collective breath held by the crowd was released as the beam found its position, cementing the completion of the installation phase. The culmination of this one-day endeavor showcased not only the progress of modern engineering, but also the collaborative spirit of the community. The Greater East Hampton Chamber of Commerce expressed gratitude to all who witnessed and participated in this remarkable event. This replacement project, which under conventional methods might have spanned weeks or even months, was efficiently executed within a single day, thanks to the innovative accelerated bridge technique. As the beams now stand, forming the skeleton of the new bridge, the future of East Hampton's connectivity and infrastructure is taking shape. The installation of these beams, though a single phase, represents a substantial leap forward in the project. The journey to replace the East Hampton Mannan River Bridge is far from over, with the deck and various other components yet to be installed. However, the installation of the beams serves as a poignant reminder of what can be achieved when innovation, determination, and skilled labor converge. The replacement of the East Hampton Mannan River Bridge is a testament to the capability of human engineering and collaboration. The once aging bridge is now making way for a modern and robust structure that will serve the community for decades to come. This monumental day of beam installations will undoubtedly be remembered as a pivotal moment in the history of East Hampton, highlighting the power of ingenuity and the possibilities that emerge when communities and technology intersect. Divided into 2 main components, the project involves transforming the conventional railway line between Incheon International Airport and Wonju into a high-speed route. This endeavor was initiated in 2014 under the guidance of KR, Korea Railroad Corporation. The comprehensive plan aimed to boost train speeds from the existing 100 to 120 km per hour to an impressive 150 to 230 km per hour. This upgrade was crucial to accommodate the influx of travelers expected during the Winter Olympics. The second part of the project was the construction of a new railway line connecting Wonju and Gangneung, managed by KR's Gangwon Regional Office. This 120.7 kilometers long line project began in 2012, focusing on the stretch between Seo Wonju Station on the Junggang Line and Gangneung Station on the Yangdong Line. By 2017, the railroad bed was nearly completed, and the final stages involved laying tracks, architectural construction, and systems implementation. Innovative engineering techniques played a crucial role in the construction. Notably, the free cantilever method, FCM, was employed for the Jucheonggang Bridge, allowing the upper deck structure to be built in segments, reducing construction challenges. The upgraded pipe roof structures method, UPRS, was applied to the Chilbong Tunnel, ensuring stability through difficult terrain, employing pre-assembled steel beams connected with rebar and mortar. The construction of the Gangneung Tunnel, a 2,860-meter-long tunnel, utilized the shield tunnel boring machine (TBM) method, minimizing civic complaints and environmental disruption. This technology, compared to traditional blasting methods, reduced noise, vibrations, and impact on the surrounding area. Moreover, the project demonstrated a commitment to localization and sustainability. KR developed a rail fastening system that eliminated dependency on imported technology, with 4 Korean companies installing 340,000 sets of fastening systems along the line. Additionally, ecological considerations were integral, especially in the construction of the Daegwallyeong Tunnel within the buffer zone of the Baekdu-daegan mountain range. A joint ecological monitoring project ensured minimal environmental damage and protection of various species.